Thank you. Thank you. Don't forget to submit your homeworks if you haven't done so already. And online students, please submit through the portal on Blackboard. We are live on YouTube and Blackboard, both of them. But we'll probably move to YouTube eventually, completely. So make sure you know how to access the YouTube link. How to have access to that link. Yes. After class? Sure, yeah. Well, that's all right. That's all right. Yeah, there were some typos on the text of the homework. I'm pretty sure you got the email from me. And even if you have used the wrong numbers from the text, you won't lose any points if you haven't seen the email or anything. So you don't really need to worry about those typos. And hopefully we won't have any of those moving forward. One of them actually was, I think, was a problem on the book. Was not even a typo on my behalf. Okay. Is there any questions about homework, about the problems we solved in the previous lecture? No? You have a question? Okay, so I think we stopped at this Buckingham Pi theorem problem. And I want to go over it again. We essentially finished it, but the last part of it remained. And I want to finish that problem, and then we'll move on to chapter 2. So let's do this. That was the problem on the Buckingham Pi theorem, which is problem number 7 of your book. The idea was the drag on the hull of a ship. This is the text of the problem. I'm going to read it again. The drag on the hull of a ship depends in part on the height of the water. Oh, not this one. It wasn't this one. I'm sorry. 1.8. The shock wave problem. I think 1.7 was your homework problem. So the shock waves on a vehicle in supersonic flight cause a component of drag called the supersonic wave drag, which we talked about wave drag a little bit. So we became familiar with it a little bit. And we defined the wave drag coefficient as wave drag divided by dynamic pressure multiplied by the span area, which is how we define all of the force coefficient. And we want to show that this wave drag CD, wave drag coefficient, is only a function of your gamma as well as the Mach number. Yeah. Okay, so we want to reduce the variables in this problem to essentially 2 independent variable and 1 dependent variable, right? The idea in the Buckingham-Pi theorem solutions problems in general was to find the variables, the main variables, the dimension variables. Okay, so let's do this. We are talking about wave drag as a function, and we talked about this part as well. Since we are in the supersonic flight, the heat capacity and temperature in general become important, so we have to include the heat capacities, Cp and Cv. The other idea was that your density and velocity are always important, as well as the coordinate. What else do we have here? We are including the effects of temperature through these two, right? Heat capacity. Also through the Mach number. So supersonic flight, Mach number becomes very important, right? So we need to include a free stream Mach number because it becomes important. Mach number itself is a function of temperature, if you recall. Okay, so these are the independent variables. Cp, Cv, rho infinity, V infinity, C. C is the chord length, and A infinity. And we also have 1 dependent variable. The first step was to move all of the variables, independent and dependent, to one side and have a new function that is equals to 0. So G of, we're going to move the dw to the other side and combine with essentially create a new function, which is f minus this d, right? Let's call that new function G. G of Cp, Cv, rho infinity, V infinity, C, and infinity equals to 0. Is there any questions up until this point? No. Hopefully you have all solved this problem in your homework without cheating. And so you know how this goes. Okay, so how many variables do we have? 1, 2, 3, 4, 5, 6, 7. 7 variables, so independent and dependent. And the other thing we have to count is the number of fundamental parameters. We have length, which is present, right? For example, in chord length is velocity. We have time, right? It is present in velocity, for example, again. We have mass, which is present in many of them. And here, in this specific problem, since we are dealing with temperature and the effects of temperature, Cp and Cv, temperature is also present. So let's call it degrees. Your book has called it degrees, and I'm going to follow your book. So these are the number of fundamental parameters. These are the number of variables that are present. How many dimensionless parameters we're going to have? 7 minus 4. We have to end up with at least 3 dimensionless parameters, which is consistent with this formulation, right? We have 1 dependent dimensionless parameter, 2 independent dimensionless parameters. Okay, so what should we do next? The next part was, let's actually do this first. Let's actually find the dimensions for each of them. The dimensions for Cp and Cv are the same. What are the dimensions for Cp and Cv? We talked about it a little bit in the previous lecture as well. Whenever you were confused about the dimensions of heat capacity, you have to go back to this very basic equation that gave you Q as a function of mass, heat capacity, temperature change, right? We have all seen this equation. This is an equation I think we have seen from high school, right? So this is This is not heat rate, so this is joules, kilogram, Kelvin, right? SI, we're dealing with SI. Joules itself is newtons multiplied by meter. We're gonna take it to the most fundamental form. Newton itself is kilograms meters per second squared. Mass times acceleration. This is the most fundamental you can get here. So joules, if you want to represent it in dimension, in the fundamental parameters, this is going to be the dimensions for joules, right? I'm going to find the dimensions for CP or CV. Both of them are the same. We have to essentially take all of these to the other side. The kilograms will go away with each other. And on the other side, we're going to get second squared per meter squared Kelvin, right? Meters squared. I'm sorry. So this is meters squared per second squared Kelvin. So this is going to be your dimension for CP and CV, which in this nomenclature is going to be length scale to the power 2, time to the power 2, multiplied by degrees. So dimensions for CP and CV. Here's the okay. We don't have a blackboard cleaner. Any questions so far? Pretty straightforward, and we have gone over this in the previous lectures. Rho infinity, kilograms per cubic meter. Kilograms is mass. Cubic meter is length to the power 3. V infinity, meters per second. Meters per second is length over time. Also, we have chord length is meters, so length. And A infinity, the speed of sound, is again meters per second. Okay. So the first thing you wanted to do was to take 3 of these parameters and 3 of these parameters and make them a main component of your dimensionless parameter, right? Which essentially means that the power of that parameter in your dimensionless variable, like Reynolds number, is going to be 1, right? If you wanted to derive the Reynolds number, that power of velocity could act as a foundational variable there with the power 1. So we're going to use, we already know that this was given to us, that like Mach number is one of the parameters. So velocity is definitely going to be there. So the power of velocity is 1. And then the idea was this pi, let's call it pi 2, because we did pi 1 previous lecture. This pi has to be a multiplication of all of the independent variables here. So rho infinity to the power a multiplied by Cp to the power b multiplied by Cv to the power c multiplied by, what else do we have? V infinity multiplied by c to the power mcd and multiplied by a infinity to the power e. Okay, let's write these in terms of their dimensions. Dimensions of the pi is 1. Dimensions of rho infinity is mass divided by, let me actually bring all of the powers to the numerator. So mass times length to the power -3 multiplied by length squared times -2 k -1 to the power b multiplied by the same thing to the power c multiplied by L time, which stands for velocity, and L to the power d, again, L time negative to the power e. Do you have any questions up until this point? This is where we stopped for pi 1, actually, not for this one. But this is where we stopped. Any questions? No? Okay, so I remember, like, someone didn't know how to go forward from this point. It's actually pretty straightforward. The idea is a multiplication of all of these has to be equals to 1, which essentially means that all of these has to be 1, right? All of these have to be 1, right? Some sort of the multiplication has to come out to be 1. So these powers have to essentially come out to be 0. That's just a mathematical thing, right? When you actually simplify them. So what does it mean? Like, we have the presence of length multiple times, right? The power of length has to be 0. We have the presence of time multiple times. This has to be degrees, not Kelvin. Degrees. We have the presence of time in many of the variables. The power of time has to be 0, right? For this side, for the left side to become 1. What does it mean? Let's start with the power of length. We have L to the -3a from here. Then this is a multiplication, so I'm just separating L, putting L's on one side, then putting M's on the other side, so on and so forth. So it doesn't really matter because we are just moving this inside the multiplication. It is not going to change anything. And the next one is L to the power 2b. See? L to the power 2c, the next one. And then we have L to the power 1, which is 1, L to the power d, L to the power e. Okay. To be, why should it be negative? No, that's 14. Yeah, that's all right. So all of these have to be equal to 1, right? Which essentially means that these powers have to be, the addition of all of these powers have to come out to 0. So we're going to have -3a plus 2b plus 2c plus 1 plus d plus e equals to 0. This is one equation. Second one, let's write it for, t. we're going to have negative 2b, negative 2c, negative 1, negative 1, negative e, right? So negative 2b, negative 2c, negative 1, negative e equals to 0. The third equation, let's do degrees. We only have it here and here. Negative b, negative c has to be equals to 0. And the fourth one, we only have the presence of m once. So m to the power a is equals to 1. So a is equals to 0. Okay. Is there any questions here? Any questions or comments? I assume all of you have done your homework, right? So do we see any problems here? Okay. So what should we do about it? I like your mask, by the way. I like your mask. Wearing the same mask. Okay, why did we get into this problem? I'll give a bonus point to whoever can point out the mistake. Choosing which variables?
When you're writing pi,
Okay.
we should choose the proper variable. In such a way, we have list parameters here.
Okay, how should we do that? So what do you, okay, how should we do that? What should we do then? Let's see, I'm getting it.
We are defining the parameter as power.
Okay.
We should choose the parameters to have 0 power. There we chose velocity as 0 power. But we could choose one of the first variables to have this parameters here.
But it doesn't really matter if you're using the proper param variable here, because whatever variable you use, we would have ended up with 5 equations, right? 5 powers, right?
So we can choose our variables here based on what we need in the question. We need gamma and Mach number.
Yeah. Yes. Okay, so what should I have done? What should I have done? That I didn't do. We actually have with matter. I'm going to give you some time to think about it and answer the question I'm getting on Blackboard. So the question is, would it matter is equation? I'm not sure if I'm reading the question correctly, but they are asking whether it matters if this is negative b equals to c or negative c equals to b. No, it doesn't matter. It's essentially the same equation. So you are on, she is on the correct path, okay? There is a problem here, right? There's a problem here. And that goes back to the way we came up with this method in general. Okay. If you recall, there was supposed to be a little bit of guesswork, right? That was the idea. That was the main idea. And the guesswork involved choosing the important variables. Let's call them important variables, right? So let's say the first thing you have to notice here is that we were supposed to have 7 variables, right? But here I only have 6. I'm forgetting the wave drag. That's first, right? So if we add the wave drag, then we will end up with how many equations? 4 equations and a cell, and then one more unknown. Essentially 6 unknowns, right? Instead of 4. So what's the problem? What are we missing? Or what should I do? Because I dropped the ball here. I should have included the wave drag, but I did not. And if I include the wave drag, yes. There are 3 pies, right? But the calculation of these pies are independent from each other, right? We don't need another pi to get the first one. Pardon me? Okay, that you are essentially correct, right? But it doesn't happen at random, right? We essentially have to drop 2 variables. The idea of choosing these important variables at random, not at random, but a little bit of guesswork, was to be able to drop 2 of them from the calculation, right? We already know from the text of the question that we have a force coefficient, gamma, and Mach number. So what are the important variables here? Velocity, or I guess speed of sound, doesn't really matter. One of the CP or CV, and the drag, the force, okay? So when we are calculating these pies, let's write them down here. V infinity, wave drag, and let's go with CV, right? These are the important variables. When we are calculating pi 2 or pi 3 or pi 1, whatever pi that is, one of them appears, one of the important variables. But the other 2 do not appear. Let's say CV. Okay, so we will end up with 4 unknowns and 4 equations. Okay, so we essentially have to remove all of the C's. So A is 0, B is 0, which means that E is 1. Okay, and this is 0, this is 0, and B is going to end up to be -2. I'm making a mistake somewhere. No, it doesn't matter. It can be pi 1, pi 2. They should have given us the same thing. So I want to calculate the second dimensionless numbers. I'm essentially calculating the same one. Okay. Okay, A is 0. From here, I'm making a mistake somewhere. It shouldn't give us D negative 2. What is D here though? It should. So we want to find the Mach number, right? So Mach number, what is Mach number? V divided by A. So the power is already here 1. It should be negative 1, right? The power of A is E. So E should end up being negative 1, which it is negative 1. Why doesn't anyone mention that? So it is negative 1. You bring this to the other side, it will be positive 1. Negative E is positive 1. E is negative 1, right? Which means that your D is going to be 0. And so A is 0, B is 0, C is 0, V is 1, D is 0, E is negative 1. Okay? So your pi 2 is going to end up being V multiplied by A to the power negative 1. These are the first three, which is the Mach number. So for the second pi, you essentially do the same thing. But for the second one, let's say you want to do the force coefficient, you have to drop the V. And then your D is going to be to the power 1. Third one, you drop the D. And also the velocity. Your CV is going to be to the power 1. Does this make sense? Does it answer all of the questions? I remember we had some questions. Oh, we have already spent half an hour on this. I'm moving a little slowly. You have to move a little faster. Okay, so do we have any questions about chapter 1 in general? About the homework, about the quizzes, or anything about the concepts, whatever. No? Okay. Good. Yes. So let's just start with chapter 2. Chapter 2 is essentially going to be the start of aerodynamics. Okay. In chapter 2, we want to learn the basic mathematics that we need to perform an aerodynamic analysis. That's the idea here. A lot of this mathematics, I don't want to say a lot of the mathematics, but some of the mathematics you have seen before. And I used to just like mention them and just ask the students to go to the book and read them. But I came to the understanding little by little that math is not our a strong leg in the department. So whenever we want to use mathematics, we have to cover it. That's why I've been covering it for the past 2 years. So if you don't know any of the mathematical operations we introduce here, make sure to ask, okay? Or like send me an email if you have any questions. Any questions? Okay. And after the mathematics, after the mathematical operations, we are going to talk about the biggest governing equations in aerodynamics, which are the conservation of mass, conservation of momentum, the momentum equation, and conservation of energy. And hopefully you have seen some sort of a representation of this in your undergraduate fluid mechanics. Conservation of mass momentum equation and conservation of energy. Okay. Is there anyone who can tell me what was the representation of conservation of mass in your fluid mechanics, in your undergraduate fluid mechanics? We have all passed fluid mechanics, right? Is there anyone who has not passed fluid mechanics? Okay, so what was the conservation of mass in fluid mechanics? We usually call it continuity equation, right? So what was the continuity equation? No one? It's constant, right? So exactly, thank you. So whatever essentially goes into a control volume or duct or whatever has to come out. That was the idea. Continuity equation, rho AV is constant. Okay. So rho AV in is equals to rho AV out. What about the momentum equation? I'm just asking this question to refresh your memory. We are gonna talk about them in detail. We're gonna introduce. We are not gonna derive the equations, but we're gonna introduce the main equation, the main governing equation in aerodynamics. Momentum equation. Yeah, it has a lot of variables. But what was the momentum equation in compressed? Yes. It is much simpler than that. Let's say you are dealing with compressible, incompressible, and the time. That's the definition, right? Does anybody remember Bernoulli's? What was the Bernoulli's equation? P plus 1/2 rho v squared is constant. Right? Do we all remember this? Okay, Bernoulli's equation, incompressible fluid flow. And in vitro assumptions, a lot of assumptions was made to get this equation. And I don't think you have gone over the conservation of energy equation in fluid mechanics, but we will see it in this course. So mathematics, first the mathematical operations we need, the mathematical operators we need, and then we're going to move on to the general form of these equations. We will just become familiar with them. We will not derive them. I probably will give you a bonus point just to go over the derivation of them and submit the derivations you're going to see. And after this, we are going to become familiar with some concepts that are only applicable to aerodynamics. Okay, and these are also mathematical equations, right? Just fundamental equations. But we're going to need them to be able to move forward. Okay. Let's just start with the mathematical operations. And let me ask you a question. What is a vector? Does it have to be force? Or is there any force that is not directed? So a magnitude and a direction, right? We have two types of representation of parameters in aerodynamics, right? A scalar, which is just a magnitude. I'm like 99% sure that you are familiar with these concepts, but we just want to go over them again just to refresh your memory. So what are the important scalars? What are some examples of important scalars in fluid mechanics, in aerodynamics, or whatever that is related to fluid? A distance. Let's call it delta x. Okay. What else? It's actually not delta x. How delta s? No. Let's actually not do the distance because we have a vector form from this representation as well. We don't want to confuse ourselves. There are some parameters, there are some, like in fluid mechanics specifically, that are coming to play in fluid mechanics or aerodynamics, and you don't see them in solids, for example. You don't see mass in solids? Yeah. Volume? Okay, volume is definitely a scalar parameter. Or is it? We're going to talk about that, okay? But yeah, okay. What other parameters? What are the parameters that are important in fluid mechanics? Density, okay? Is density a scalar parameter? Yes, okay. That's the first one we can say with certainty. Density is a scalar parameter. What else? Is temperature a scalar parameter? Yes, doesn't have any direction. What about pressure? Is pressure a scalar parameter? We have one no. Let's take a vote on it, actually. Who goes for temperature? Who votes for temperature as a vector? And who goes for a scalar? Let's do vector. One vector. You have to be able, if you want to vote for any of them, you have to be able to elaborate. Who votes for a scalar? Okay. So why is this a vector? What about others? You don't have any opinion? No? Okay, I guess no. Why is pressure a scalar? Let's go with the scalar first. We have like a couple of people.
I think it's a scalar because it pushes in all directions.
Okay, a scalar because it pushes in all directions equally. Pushes in all, let me write down this. Pushes in all directions equally. Equally. What about the vector? It has to go in a direction. Okay, so it has direction. You wanted to add something to the scalar? No? So vector, it has a direction. Okay. This is an interesting topic. I always bring it up in my classes. And it is always a source of confusion. It used to be a source of confusion for myself as well when I was a student. Okay, let's see. From the people who have not voted yet. Okay, I need some input. A scalar or vector? Because it has a direction? Okay. Who else? So you change your vote? Okay, pressure vector. Okay. So we are moving the needle. Who else? You guys have to start talking, and we're gonna spend the next 30 minutes just like this.
I think it's a vector.
A vector, okay, because of the direction. Do you guys have any opinion on the matter on this side of the class? You have one person online. It depends on the scope of your system. You have to elaborate. So we have one of the online students is telling me that it depends on the scope of the system. And I'm not sure what that means. So you have to elaborate. Anyone else? Do you have any opinion? Both of you, right? Doesn't matter. A scalar. Okay. Okay. I think we have had enough compelling argument from both sides. Pressure, we define pressure as the force per unit area that is normal to your surface, right? That's the definition of pressure in fluid mechanics, or I assume anywhere else, right? But it is always normal to your surface, right? Exactly. Thank you. Thank you. What's your name?
Jason.
Jason. You're going to get a bonus point. I like that answer. Jason, send me an email. Right. Okay. So the surface is the thing that determines the direction of pressure, not the pressure itself. It has to be normal to the surface. Okay. And mathematically, we define pressure as force per unit area, right? Which is essentially, if you want to play mathematical games with it, it has to be the dot product. We're going to talk about the dot product. If you don't remember what dot product is, of area, force, and inverse of the area, right? So the dot product of two vectors is always a scalar. So mathematically, we can prove the pressure is a scalar, and area, the source of the confusion always comes from the fact that people don't really assume that area is a vector, but area is a vector, right? From a mathematical perspective. We're going to talk about this. Okay. So a scalar, density, temperature, pressure. Okay. Vectors, what are the important vectors in fluid mechanics? Or let me rephrase the question. What is the most important vector in fluid mechanics? Velocity. Velocity vector. Exactly. Thank you. Okay, so I'm pretty sure we are all familiar with the basic operations we can do on vectors, like addition, subtraction, and all of those basic operations. Right. The addition of two vectors is a vector, another vector C. If you do represent, let's say these are your two vectors, vector A and B. The addition of the two goes from like the starting point of A to the ending point of B. Subtractions is essentially the addition. The only difference is that instead of vector B, you're going to have a vector negative B. The difference between vector B and the negative B is the direction. So vector A, exact same vector B in the other direction. So your vector C is going to be this. And then we have the multiplication, which is where things become a little more complicated, but I'm pretty sure you have seen this before. We have two types of multiplications when it comes to vectors: dot product and cross product, or the scalar product and the vector product, cross product. Both of them are used many times, or used a lot in aerodynamics, right? The dot product of two vectors is always a scalar, we can calculate the value of this scalar by taking the magnitude of each vector, multiplying them, and then multiplying them by the cosine of the angle they make with each other. So essentially, you're going to get the maximum value for the dot product if the two vectors make the angle 0. But cross product is always going to give you a vector. We can find the magnitude of this vector as the multiplication of the magnitude of the two vectors and multiplied by the sine of theta. Or we can actually define the resultant vector as this magnitude sine of theta multiplied by a normal vector, unit vector E, that is normal to A and B. Any questions so far? Okay, so we are all familiar with these concepts. Do we know how to calculate the magnitude of a vector? Is there anyone who can tell me in Cartesian coordinate system? Let's say you have vector xi, bj, zk, Cartesian coordinate system, and you want to calculate the magnitude of this vector. Like the square root of x squared plus y squared plus z squared, right? That's it, the magnitude of the vector in Cartesian coordinate system when you have x, y, and z. But the main coordinate system, we define 3 different coordinate systems that we are going to use in aerodynamics. And all 3 are actually used very often. It is not like your other courses that Cartesian coordinate system is the main system and the other 2 just are introduced. All 3 systems are very important in aerodynamics, in flight mechanics, and especially in orbital mechanics, because in orbital mechanics, you're only dealing with the spheres, right? Or a lot of curved movement, curved path. So Cartesian coordinate system, cylindrical coordinate system, 3 main ones that we have seen. A spherical coordinate system. Your Cartesian coordinate system, you essentially have 3 main axes, x, y, z. Each of these axes are defined by a unit vector. X is defined by I, j for y, and k for z. So any vector A in Cartesian coordinate system will have this kind of components, x component in I, y component in j, and z component in k. Cylindrical coordinate system, we have r, theta, and z. They're essentially inside the cylinder. Your r is the distance from your coordinate. Theta is how much you have moved. You can have rotated. And z is going to be your height. We can relate these 2 coordinate systems with these equations if you had to convert them. X is equal to r cosine of theta, y is equal to r sine of theta, and z is essentially the same. If you want to go from the other way around, r is going to be equal to x squared plus y squared, and theta is going to be arctangent of y over x. Just mathematical definition. And in cylindrical coordinate system, we can represent each vector A as r, E of r. Unit vectors in the cylindrical coordinate system are going to be E of r, r, E of r, theta, E of theta, and z, E of z. Any questions here? In a spherical coordinate system, we're essentially dealing with a sphere that's going to surround your thing. You're gonna have R, then this movement is gonna be phi, and you have another angle theta. So R, theta, and phi are going to be your main axis here. We can relate this to your Cartesian coordinate system as R sine of theta cosine of phi is going to be equal to X. Y is going to be R sine of theta sine of phi. And Z is going to be equal to R cosine of theta. R here is going to be a square root of X squared, Y squared, Z squared. Let me actually write them down. And theta is arc tangent arc cosine of Z over R, and phi is going to be arc cosine of X over a square root of X squared plus Y squared. So hopefully we have seen these coordinate systems before. This is nothing new to us. Again, this part of the chapter is just a memory refreshment, just to make sure we are all clear on what's going on. So based on these coordinate systems that we have defined, we can actually find the dot product and cross product, or a scalar product and the vector product. Your dot product is in Cartesian coordinate system is going to be, let's say your A, let's see, okay. Let's say your A is A of X, I, A of Y, J, and A of Z, K. Let's say we have the same thing for B, B of X, I, B of Y, J, and B of Z, K. Your dot product is going to be AX, BX, AY, BY, AZ, BZ in Cartesian coordinate system. And I mean, in any coordinate system for that matter, the only difference is going to be that you are going to find the components based on different axes. Like in cylindrical coordinate system, your vector A is going to be A of R, E of R, and then E of theta, E of Z. I forgot to mention the unit vectors here. E of R, E phi, E theta. Is there any question so far? Okay, is there anyone who remembers how to calculate the cross product? Other than the formula we just had, using the magnitudes, yes. Cramer's rule. What was the Cramer's rule? Let's tell me what to write. Don't remember? Okay. Who remembers? Okay. So let's say we are dealing with the Cartesian coordinate system. Your first row, we are gonna have to have a matrix, right? IJK, and then okay, so we're gonna have to create this matrix and take the determinant of this matrix. That's it. It's going to be the same thing for the other coordinate systems. Instead of I, J, K, we're going to have ER, for example, for the cynical, ER, E theta, EZ, A of R, A of theta, A of Z, and so on and so forth. Okay, well, how do we take the determinant of a matrix? If you remember, I'm just going to write it down. We take it the determinant of this smaller matrix first and multiply it by I, which is going to be AI BZ minus AZ BY I. Then we take this and take the determinant of this matrix. This is a smaller matrix. So AZ BX minus AX BZ J. And there's a plus sign here, also plus. Then we take this third one and take the determinant of this matrix. So it's going to be plus, I'm going to write it up here, AX BY minus AY BX. Okay. So that's how you calculate the cross product. That's how you take, and there is another way to take the determinant, but you can actually, there are many ways to take the determinant. You can use any method you are comfortable with. Doesn't really matter. Okay. Any questions so far? Just memory refreshments, hopefully. Okay. The next step is going to be the introduction of del operator, or the Nabla Greek letter. Okay, who can tell me what the del operator is? Del operator. Pardon me? Can you repeat what you said? It can be, if you multiply it by a scalar, it will be the gradient of whatever, right? But what is the operator itself?
It's derivative of a vector.
So it is the derivative vector, right? How many people have not seen this before? Hopefully none. The del operator, right? You may not remember what it does, but hopefully you have seen this, right? So this is the derivative vector. Okay. In Cartesian coordinate system, what it means is that we're going to get partial x I, partial y j, and partial z k. The derivative vector in Cartesian coordinate system. Okay. And it is going to be a different vector in other coordinate systems. I mean, it is going to be the derivative vector, but the derivative is going to be a little different in other coordinate system, and we're going to get to that. So let's multiply this by a scalar. Let's do pressure, right? Since this is a vector multiplied by a scalar, we don't have the dot product or cross product, right? Because this is not a multiplication of two vectors. This is just a vector by a scalar. So what happens when you multiply a scalar by a vector? Exactly, multiply every component of this scalar, a vector, by that scalar. So this is going to be equal to partial P partial X, which is the gradient of pressure in X direction, or changes of pressure in X direction, I partial P partial Y J, and partial P partial Z K. Okay, this operation is called the gradient operation. So whenever you multiply this del operator by a scalar, you are essentially taking the gradient of that scalar. And what it does, the solution is going to be end up being a vector. So taking a gradient of a scalar is going to create a vector. Does it make sense? Okay. Okay, and this is in Cartesian code. I'm gonna write down the same things for cylindrical. I'm just gonna write them down. But what will happen if we are dealing with what will happen if we are dealing with two vectors? So one, the del operator is a vector by itself, and the other one, let's say, d vector in fluid mechanics or aerodynamics, which is the velocity vector. We're gonna have two different forms of multiplication. One is going to be del dot v. The other one is going to be del cross v. This operation, what is this operation called? Divergence. So taking the divergence of velocity. This one was called the gradient, taking the gradient. Multiplying, doing the dot product of the del operator and a vector is going to be called divergence. So here we are taking the divergence of velocity. Divergence of velocity. So taking the divergence of velocity is going to transform that vector to a scalar, because that's what dot product does. So we're gonna get partial v partial x plus partial v partial y partial v, or the component of v. Let's call it vx, vy, vz, partial z. Okay? And in aerodynamics in general, vx, we use u for it. So the component of velocity in the x direction, the component of velocity in the y direction is a small v, and the component of velocity in the z direction is called w, right? So essentially, this divergence is going to be partial u partial x plus partial v partial y partial w partial z. Okay. What about this next operator? What do we call this? One, curl. So taking the curl of a vector is essentially means that doing the cross product of the del operator and that vector. In Cartesian coordinate system, it essentially means that taking the determinant of this matrix. Okay. So what will be this? What will happen to these operations in the other coordinate system? In the spherical coordinate system, you're gonna get, for gradients, you're gonna get partial. Let's say we are taking the gradient of pressure in the cylindrical coordinate system, partial p partial r. Then you're gonna get 1 over r, partial p partial theta, and partial p partial z. And I forgot the unit vectors, er, e theta, ez. taking the divergence in the cylindrical coordinate. I'm going to write that here. Again, taking the divergence in cylindrical coordinate system is essentially going to be a little different. 1 over r partial r of r VR, the component of velocity in the r direction. Then for the next one, we are going to get the same thing. 1 over r, right? Yeah. Partial v theta, partial theta. I don't usually memorize this myself. I always go back to the text. You don't need to memorize them as well. Yep. Okay. And then for the spherical, let's actually do the curl in the spherical coordinates. So this is cylindrical. I know when you're dealing with math, this is del dot v. You're taking the divergence. Sorry. Here, when you're dealing with mathematics, it gets a little boring. I understand that, but there's no way around it. And since we are actually just mentioning this, right? We are not going inside any of these analysis. So just bear with me, and hopefully we will pass through this. Partial r, partial theta, partial z. And we have VR, r, v theta, and vz. So this is the curl of velocity in a cylindrical coordinate system, divergence of velocity in cylindrical coordinate system, and the gradient of pressure in cylindrical coordinate system. For a spherical, all of these equations on your text are in your textbook, so I'm not going to write them down on the board because it takes a long time. But my expectation is you go and see these equations and use them. You don't have to prove anything. Just whenever you were asked, you just have to use that equation to check the divergence or gradient or whatever in coordinate system. Does that make sense? Okay. So we're going to solve some examples on this. One thing that we need to talk about, actually, how much time do we have? We don't have that much time left. But let's talk about this part. Let's talk about the different approaches we have in solving problems in aerodynamics, right? In aerodynamics, we have, as I said, we have 3 main equations: the governing equations, conservation of mass, momentum equation, and conservation of energy, which we will talk about on Wednesday in more detail. But how do we apply that to a problem? Let's say you have the equations written down. How do you apply that to a problem? There are 3 different approaches, and each approach actually depends on the scale of the problem you are dealing with, or the perspective you want to look at your fluid, the perspective you want to use to look at your fluid. And also, there is 2 classifications. So essentially, we have 6 different methodologies that we can use to approach a aerodynamic problem to be able to analyze. The first one is defining a finite control volume. Do we know what a control volume is? Essentially a volume in a space, right? It can be any volume. It is arbitrary. It can be anything, right? And then you take that volume, you apply the conservation equations. What does it mean? Conservation of mass. A volume has 8 sides, right? In each direction, whatever goes in has to come out. Pretty simple, right? You calculate whatever is going in, which is usually rho AV. A is the cross section of each side, okay? And so on and so forth. You do this for momentum. You write the momentum on each surface, right? And based on the directions, you just have to write the force balance for momentum, right? Sigma F in the x direction, which is the forces that are being applied in the x direction, right, to your volume, to your big volume, arbitrary volume, and that's it, right? The same thing. You do the same thing for energy. The difference between like energy momentum and conservation of mass equation is that you won't have any mass generation inside your a small volume. That doesn't really make any sense for from our perspective. But from a force perspective, you have two different types of forces that are going to be applied to your volume: body forces, surface forces. We'll talk about those later in more detail. But that's your first perspective. Like, take a volume in space, a random volume. The reason I'm not using the board is because I want to show you how arbitrary this is. It's just, it has to be an arbitrary volume in space. Write the equations for each side. The conservation is pretty. It may look very complicated, but it's actually pretty easy when you get a hang of it. Right? Conservation mass, m dot in, m dot out. That's it. There is nothing else to it. And so there are two different perspectives when it comes to this concept, to this control volume approach. Actually, you can assume your volume is just staying there. It is fixed in a space, which is the thing that I just described. All of the equation and all of those things. So the fluid is coming in and going out, m dot out, m dot in, right, on each surface. There is another perspective that moves with the fluid. So the first one is called the Eulerian perspective, right? You have a fixed volume in space, one approach. The second one is called the Lagrangian perspective. It is moving with your fluid, right? Then you can make this is the integral analysis. I'm hoping you have seen this analysis in your fluid mechanics. Have you seen this type of analysis in your fluid mechanics? No. We have one no. You saw it in heat transfer. Okay. Have you seen this in heat transfer? You don't need to remember it. You just have to remember seeing it.
I've seen it somewhere.
Okay, that's a start.
It was in this building, so I guess it was.
Okay, that's good. That's good. So, and the other perspective that you haven't seen, and we're going to see in this course, is when you make this control volume infinitesimally small, so very small element inside your fluid. You can write the same. You can have the same perspective. You can have the same look at that small element as you do to the big, huge control volume. The only difference is that you are dealing with the derivatives, right? Instead of changes, right? Instead of delta P, you're going to deal with partial P, right? That's the only difference, honestly. And then that we can have Eulerian approach or the Lagrangian approach as well. So that a small element of fluid can move with your flow, or it can be fixed, and then the particles can come into that volume and can move out. We can make this smaller. We can make it a molecular dynamic, a molecular approach. Essentially, you can look at each particle of fluid, or you can have a fixed surface that particles of fluid can pass through. So instead of movement of a continuous liquid or gas, we are dealing with the movement of separate particles. And that will be the basis of kinetic theory of gases, which is out of the scope of this course, but it is a very interesting topic. And we use a lot of conclusions of that molecular approach, actually, in fluid mechanics, heat transfer, aerodynamics, in anything that deals with thermofluids. Okay. So using these, we're going to derive, we're not going to derive the equations. I'm going to give you the equation, but you are going to derive them for a bonus point. But I'm going to tell you what to do next lecture, and you will have a week to do it. Is there any questions? Whenever you guys move your hand, I just jumped. I think you're asking a question. I'm a little jumpy. Any questions? Okay. So my expectation is that you understand divergence, gradient, curl. You understand. You don't understand. That's okay. This is the normal vector, like I, J, K, which are the normal vector in Cartesian coordinate system. This is the normal vector in like cylindrical coordinate system. That's E of R hat, E of theta hat, E of Z hat. for cylindrical. For spherical, we're gonna get E of r hat, E of phi, E of theta hat, and E of phi hat. Okay, does it make sense? Unit, yeah. What did I say? No, yeah, unit vector. Sorry, unit vector. That's what I meant. Yeah, I'm sorry. But these are essentially normal, or depending on, but unit vectors. Yeah. Any other questions? So if you don't have any other questions, that's it for today's class. We are moving a little slower than expected, so I may pick up the pace a little bit for the next lecture. And yeah, if you haven't submitted your homework, this is your last chance. Make sure you submit it before. Okay. I would rather, if you're a face-to-face student, I would prefer you submit it in class.
This is actually the first time I've been able to do this since I did have COVID, and I was
Okay,
so I really didn't know, and I saw there was a submission online, so that's what I did.
that's all right. No worries. Yes.
The last question, I used Excel.